So I do want to kind of look at one thing when we're talking about work. And we did say that work and energy are related. That energy is the ability to do work. So I'm going to do a graph here. And we looked at the idea that work was my scalar product of my force and a distance. And if I looked at the magnitude, that was going to be F the cosine of my angle. So that's one approach to work. But if I do a force versus displacement, and we could actually look at this as a spring. Remember my spring equation, Hooke's law. Hooke's law was equal to a negative spring constant times x. And if I'm doing this for a spring, we get our line here because this is of the form y is equal to mx plus b, just so happens that b is 0. The negative is a restoring force, which is why we have that. But I get this displacement. Well, it turns out that the area under the curve, and this area under the curve, is equal to the work. And yesterday we saw that the potential energy of the spring was equal to 1/2 kx squared. But if I look at this area here, I'm going to rewrite this. I'm going to look at my force. There's my force, and then I have x. So this is my force times x, and my area, this is the area under the curve. We know what my force is. That's my kx. If I'm looking at my magnitude, there's my x, and there's my 2, and these two are equal. So you can actually see that the work under the curve is equal to our potential energy of our spring. So that's kind of a nice handy thing because we can extend that to be something like this. I could have nonlinear forces. So I could have my nonlinear forces. And if I want to know the work done, I'm just looking at my area under my curve if I'm doing a force displacement type plot. So that's a real handy thing that be able to do. You can actually look at your forces and your work by looking at those things. Okay, so let's look at a spring. So first of all, we're going to start with a spring on a platform. And we're going to put a mass on my spring. And that's going to compress my spring. And we're going to compress the spring. We're going to do it 0.25 meters. And the mass that I put on this to test my spring, the mass we're going to say is equal to 0.75 kilograms. All right. We want to know what the spring constant is. Well, I can use Hooke's law. And we know that the magnitude of the force is going to equal my spring constant times my stretch or my compression. So I'm going to get the magnitude of the force divided by X is going to give me my spring constant. This is going to give me mg divided by my X. We know that the mass was 0.75 kilograms. Gravity is 9.81 meters per second squared. So I have a Newton on top, and I have my meters at the bottom. So we've got that. So let's do that calculation. I've got 29.43 Newton meters. We're just going to make it approximately 29 Newton meters. So we've actually measured our spring constant. So we're able to actually calculate the spring constant. So we're going to take that same spring.
I have a question.
Uh-huh.
When we write Newton meters, do we have to put N divided by M, or can we just put NM?
Well, this is Newtons per meter.
Okay.
Are you talking about this?
Yeah, I think when that turns into joule.
This one will turn into a joule.
Okay, okay.
Because this is a Newton divided by meter. And the reason we do that is because we're doing force per distance.
Yeah.
Because you could actually, this is actually also equal to kilogram second squared.
Okay. Thank you.
Yeah. And that's why the unit analysis helps to make sure you're doing your equations correctly. Because if you get this and that's what you're intending to do, you probably set up your equation wrong. We're getting an alert here. I'm surprised my phone didn't go off. My husband's phone went off, and same phone, but no telling what's going on. Okay, so we've got that there. So we're going to take the same spring, and we're going to change it up this way. All right, and we're going to put a ball in front of it. We're going to compress our spring 0.5 meters. And we are going to have the mass of our ball here is going to equal 0.5 kilograms. We're going to let it go over a frictionless surface, and then it's going to hit a rough patch. Okay. It's going to hit a rough patch. And this is going to be frictionless through here. And then we want to, so I've got a ball, I've got my rough patch, and we're going to lose do something real quick. We're going to lose 20% of the energy. We want to know the final velocity. At the end. So we know the potential energy of our spring is going to equal the total energy of the system. which is going to equal the initial kinetic energy. And so that part, we've got all of that. The final velocity is going to be the total energy minus the lost energy, which is going to equal our new kinetic energy. So our potential energy of the spring is going to be 1/2 kx squared. We had our K was 29 newtons per meter. Our X is 0.5 meters, and it's squared. So our unit analysis gives us Newton meters squared divided by meters, which gives us now our Newton meters, which gives us our joules. So we've done that correctly. So our total energy for our system is 3.6 joules. And that's going to equal our initial kinetic energy. So now I've got my total energy minus our lost energy is going to equal 1/2 mv final squared. So this is going to be 2 divided by the mass of my 3.6 minus, we lose 20% of our energy, so it's going to be 0.2 times 3.6. This is going to give me my new v squared. And so 2 divided by 0.5 times 3.6 minus 0.2 times 3.6. And if I've punched it into the calculator correctly and everything else, I get 11.52. And this unit here, this was joules, so this is in Newton meters. This is in Newton meters, so we're okay there. And then I'm going to divide by kilograms. So if I have kilograms, meters, meters squared divided by kilograms, that cancels, that cancels. I end up with meters squared, seconds squared. So that's good. So my velocity is going to just be the square root of that. And it's going to be 3.3 meters per second. So we can use that information to get us a little more complex of a problem. So let's look at work as for tools, because we use tools because it helps us out. So let's look at work in relationship to tools. So one tool we have is a lever. And in my lever, I have a fulcrum. And now I want to lift my object or my box. And let's say that this has a mass, and our mass is going to be, let's make it 15 kilograms. And we want to lift it up 2 meters. The amount of work done is going to be our force times our distance. And that's going to be our 15 kilograms times 2 times 9.81. And that'll give us in joules. So we get 30 times 9.81. Gives us 294.3 joules. So that's the amount of work done to lift the box. But let's say I want to apply a force here, and I'm going to use my lever, and my lever, I'm going to actually push through 3.5 meters. What's the force that I have to apply? Well, it doesn't matter whether I'm on this side of the lever or I'm on this side of the lever, the work to lift has to equal the work to lower. Well, we know that's 2.94.3 joules. This is going to be the force times my distance. So I get my 2.94.3, and that's my Newton meters. I'm going to divide by my meters, which is 3.5 meters. Meters will cancel. And I get that the force that I have to apply is only 84 newtons. So if I'm wanting to lift this up, I have to apply 294 joules. But if I just want to use my lever, I only have to apply 84 newtons. All right, I only have to apply. This would be, if I'm looking at my newtons here, it's 15 times that. So let's look at my 15 times my 9.81. That's 147. This is 147 newtons. And I only have to apply 84 newtons. Boy, that makes life a lot easier for me. So my lever does that. My ramp does something similar. So if I have a ramp, and my loading dock is 2 meters, I've got that same block here, and I'm going to move that block up my ramp. Okay, and I'm going to actually make this a 20-degree ramp. So let's find out the distance that I have to move it. Distance is going to be cosine of my angle is equal, no, that one with the sine of the angle. Sine of the angle is equal to 2 divided by the distance. I'm solving for distance. The distance is going to be 2 divided by the sine of the angle. That's 2 divided by sine of 20 degrees. So the distance that I'm going to move my block that's going to be 5.85 meters. If this is my 15 kilogram mass, which we already know that mg is going to be 147 newtons. We already figured that out. We already figured out what this work was because we did the same thing, right? We know because that's the number that we just used here. The work required is going to be 140, or it's going to be 294.3 joules. Well, this is going to be my force, but my 294.3 joules is going to be the force times my distance. My distance now, because I'm using my ramp, is going to be 5.85 meters. So that's Newton meters. Let's cancel. This is my new force. And this would say that I only have to apply 50 newtons to do the same work that I would do as if I had to lift it up. So that shows you how tools can really, really help us. So let's calculate, let's take this same problem and let's calculate the power. let's say it takes us 40 seconds to do this. Power is going to be the work divided by the time. So the work that I did was 294.3 joules divided by 40 seconds. And my power, which is now going to be in a unit of watts, that gives me 7.4 watts. So that gives you an idea of how to utilize that. All right, one more thing I want to cover is we want to look at, so let's take two balls. This ball has a mass of m. This ball has a mass of 4m. We're going to start out at a height of 5 meters. We want to look at the kinetic energy at the bottom. And we want to compare that with those two objects. All right. So at the top, the potential energy at the top is going to equal mgh, which has to equal the kinetic energy at the bottom. So for this ball, for ball 1, I get mgh is equal to 1/2 mv squared. Those m's are the same. V is going to equal the square root of 2gh. Guess what happens over here? For ball 2, I'm going to get 4mgh is equal to 1/2 4mv squared. Those cancel, and velocity is just going to be the square root of 2gh. So you kind of need to think about, when we're dealing with our conservation of energy, just because this one has 4 times the mass doesn't mean we're going to be at a different velocity at the bottom. Now, where that will come into play is this. If I have this ball and I've got a friction surface, we know that this is going to be mg, and my normal force is equal to mg. I'm going to have something that's different if I'm at 4mg. My normal force is going to be 4mg. So it will come into play if I'm dealing with friction. I'm going to have some differences associated with friction. So you will see a few things that are dealing with that. So I'm going to flip through the book here. I want to make sure that we've covered everything. talked about our spring potential energy. We've talked about our conservative forces and our non-conservative forces. We've looked at our work and our work energy theorems. And we've looked at power. So I think we're in good shape. Question: